the review. Okay, let's start and let's see what we have in section 11.5. So far, we were talking about the infinite series with the positive terms, okay? But we also know that we may have something like this, for example, okay? That means we may have a part of the formula which is -1 to the power of n to the power of n minus 1, depends. And then the terms alternate, which means some of them are positive, some of them are negative, and probably is every other term. That's actually good, good pattern. Okay, but the point is some of the terms are negative terms. That we do have a special test to check the convergence or divergence, okay, of this type of test. Let's see what we'll have. Let's look at the first one. Okay, the first test is -1. I mean the first formula, the first infinite series. It's -1 to the power of n minus 1 over n. Of course, the summation from 1 to infinity. The first term is 1, and then the second term is -½ because if I will take n to the power of odd number, of course I'm getting negative. But just the main value, the absolute value of it, is just 1/2, 1/3, 1/4, 1/5, and so on. But every other term, of course, is negative. So what I will do, looking at this formula, okay, for now, I will call maybe b sub n, which will be the main part, the main values, which is just 1 over n. Of course, we do have this alternating part, but this is 1 over n. Okay, and as I said, 1, 1/2, 1/3, 1/4, and so on. And looking at this b sub n, I would like to see that all of the terms are positive. Yeah, that we can see 1/2, 1/3, 1/4, and so on. Yes, we're not looking at the signs, just at that term. They are definitely positive. Now, I have to make sure that the behavior at infinity of these terms, okay, 1 over n, 1 over 2, 1 over 3, 1 over 4, and so on, of course goes to 0. That means this is important condition to check, this is important condition to check. And the third one, I also have to check that my formula is decreasing. And we know what to use for decreasing. The proper way to check is to use the derivative, but we can definitely see that the terms are getting smaller and smaller without any additional weird patterns. Okay, that means these three conditions are the conditions that we have to check if we see the alternating series test. Okay? The main formula is the values are positive, limit at infinity is 0 and is decreasing. And then if this alternating series satisfies all of these three conditions, we can actually conclude convergence. I can say that my infinite series, the original one, of course, with this one, with the -1 to the power of n or n minus 1, then I can say that this infinite series is convergent. And we will call alternating series test. Okay, I have the summary page I can show you, but these are important because as soon as the formula b sub n satisfies this, and we do have the alternating part, because that's the point, then we will definitely get convergence. We don't know exactly what is convergent to because this test is not giving us that. This is not a tool to get that value, but it's definitely convergent. Okay? But I'm testing this because sometimes we can get confused. I'm testing this formula for 1, 2, 3 hypotheses, 3 conditions, just because I did have the -1 to the power of n or n minus 1 part. Okay? That means I am actually using the alternating. We can't really use the alternating series test if the series is not alternating, okay? That means this is the test. Yeah? Just testing this, we have to see 3 check marks, then we can conclude convergence. Let's look at my second example. Okay, this was the first one, this is the second. We also have -1 to the n, it's definitely alternating, but let's look at the b sub n formula, the formula without this, which is n over n plus 1. Okay, I can definitely see that b sub n is positive, because if n is the positive integers, this will always give me a positive value. Now let's check the behavior at infinity. And I'm just following my guidelines from above. N over n plus 1. Okay, and what is this limit at infinity? N over n plus 1 at infinity. We do have the same degree of the polynomial, n. If it's the same degree, we can take the ratio of the leading coefficient, which is 1. That's 1. And 1 is actually not 0. That means I did satisfy this one, but I do not satisfy that condition. Okay? But the thing is, if we're not satisfying one of the condition of this test, this means that we actually, too fast, we actually not really using alternating series test. Because one important note is we can use alternating series test to conclude convergence only. Right? Because we do not have additional tools to say, oh, it's divergent. This is an example to showing you that if we're not satisfying one of the conditions, this means that AST, alternating series test, is not a good test. But actually, if the limit is different than 0, we will conclude divergence based on test for divergence. That means this infinite series is divergent, okay? And I can say by test for divergence. We remember the first section about infinite series. But please remember, we can't conclude divergence because that's the common mistake. Okay, and let's see. That's actually the test. Having alternating series, okay, which we can see -1. We always have to see that part. Okay, and the main expression, the main formula that will give me my values, except the alternating one. And we're looking at this formula and testing. Must be positive, limit at infinity 0, and decreasing. Then we can conclude convergence. And only convergence. If we're not satisfying this condition, the test is not really helpful. We have to throw that test away for a moment and use different one. Okay, and let's actually see how this works. I copy nice graph from your textbook. I really like this graph because it's like visually we can see like the proof. Let's see what we have. The pink lines are representing the terms. And that we can see b sub 1 is here, and of course on the number line we have the partial sum. That means b sub 1 is s sub 1, because if I take first term, that's my partial sum. Now I know that my next term must be smaller. Yes, do you remember? Decreasing each term, each pink line, it's shorter and shorter and shorter. This is definitely showing me that the b sub n is decreasing. Okay, this line, it's b sub 1. Then I will be subtracting b sub 2, then my partial sum is here. Okay, as we can see, I go from here and then to here. I will not mess up. And then again, my b sub 2, and then adding, because this has a subtraction, then addition of the shorter one. Then I jump here, and then jump here, jump here, jump here. That means all of the partial sum are definitely oscillating between a finite sum. Okay, that means this will be the sum. This means that the alternating series is convergent, like converges to that number. But we can see b sub n, it's definitely decreasing and must be positive. Must be positive because we don't want to have negative values. Negative and negative will give me positive, then I will mess up my alternation. And of course, limit at infinity must be 0. It's kind of similar condition to the decreasing. Okay? A little bit different, but 0. In all of the terms, they have to approach 0 at infinity. And that we can see nicely the oscillation. That means if we satisfying one more time, positive, 0, decreasing, then it's always it's the infinite, the alternating series is convergent to the sum S. Okay, really nice graph. Okay, and actually we did, I proved this one on my first slide because it's the same thing. I can maybe do one more time. Looking at this formula, we can see that the main expression, the main values are defined by 1 over n, and this is definitely positive. Limit of b sub n at infinity is definitely 0. And of course, the next term, it's smaller. And that's how I can define using this notation, decreasing. Decreasing. Check, check, check. Then I can conclude that this is convergent. This infinite series is convergent by alternating series test. Okay, I mean, that's pretty much straightforward, but we have to remember to check this. Okay? Like sometimes students are asking me why 1 over n, it's divergent. Because looking at 1 over n, I can say, 1 over n is positive, limit 0, decreasing. But of course, this is not alternating series. That means this is harmonic, okay? Harmonic series. I am not even allowed to use that above test because I do not have this alternating part, okay? That means this is definitely divergent. Harmonic series. Okay, that means just remember we can use AST if we do have this part. Okay, and let's see what else I have. This is just just showing the another like graphical explanation of the above series. That we can see a sub n are just the terms, like -1, positive 1/2, -1/3, positive 1/3. That means they are getting smaller and smaller, but that's actually the terms. And these are the partial sums. That's when I add -1/2 and +1 minus -1/3 plus 1/4. That means we will be getting small, the terms will be oscillating, okay, between S, the finite sum. Because the sum will be getting smaller and smaller and smaller, but that's depends on the highest and the first and the second value. Okay, that means that's just the approximation, and we can approximate this around 0.7. Probably in the after midterm 2, we will have a little bit more tools to get these values a little bit more precise. Okay, but for now, we have to just determine whether it's convergent or divergent. Okay, let's look at this one. Let's solve a few problems using that test. Determine whether the following series converges or diverges. -1 to the n, great, I can use my AST, 3n over 4n minus 1. It means I can see right away that the formula b sub n is just this. Okay, and I can maybe use this. It's definitely positive. Let's check a behavior at infinity, limit at infinity of 3n over 4n minus 1. And now, do you think you can tell me the limit? 3n over 4n is, yes, thank you. It's just simply 3 over 4, which this means is not 0. We not satisfy this condition, but please remember, I can't say the infinite series is divergent by AST. No, I can't say like that. Again, we fail the limit. Okay, the limit is not 0. If the limit is different than 0 or the limit doesn't exist, I can say right away, this is divergent by test for divergence. Okay? Please remember, not the AST. And I will not even check. I think it is decreasing, but we don't even have to finish, because it will be, if we will get the derivative, we will definitely prove this. But we can see, that's the point. We can't really use that. I mean, I can say alternating series test is not a test because we can't use it. We can only use when it works. Maybe this way. We can't conclude the other way. Otherwise. Okay. Determine whether the following series converges or diverges. -1 to the n, of course, it's alternating one, n squared over n cubed plus 1. That means my b sub n formula without the alternating is this. Okay, and n is positive, then the entire formula is positive. Limit at infinity n squared over n cubed. Of course, is 0. And denominator is like growing faster. This will be decreasing. The next term is definitely smaller. You may use the derivative to prove it, but I will skip the differentiation for now because we're focusing on the new stuff. Decreasing. Excellent. I can definitely say that this infinite series is convergent by alternating series test. Everything works. We do have the alternating part. Actually, I can make, okay, that's me, definitely everything is correct. Okay, let's maybe do one more. Oh, I thought that okay, we can do, I have this one. Let's do this one. Okay, infinite series -1 to the n minus 1, natural log of n over n. So we can see this part is the alternating part. The main formula is natural log of n over n. If n is positive integer, this is always positive. And actually, let's remember, let's start from 2, because natural log at 1 is 0, and I just want to avoid 0. Okay, and then limit at infinity of the ln of n over n is of course 0, because denominator is winning, function n grows faster. And now natural log of n over n, I think it is decreasing, but let's actually find the derivative. Ln of x over x, we remember we have to rewrite in terms of x, and then let's differentiate. I'm looking for the intervals of decrease of this function. I will use the quotient rule. Natural log of x, derivative is 1 over x times x minus ln of x times 1 and x squared. This means derivative looks like 1 minus natural log of x. Okay, and I want this derivative to be less than 0. I have to check the intervals. I will ignore a denominator because it's always positive. It means only top. This has to be less than 0. Let's say we add ln of x to both sides. 1, it's simply ln of e, and I can drop natural logs, and I can actually switch. That means, oh, too fast. For x greater than, oh, no, let's, okay, I will leave it like that. For x greater than e, this expression is less than 0, which means the entire derivative is less than 0. Then function is decreasing. That means, do you remember, it's decreasing from starting from e. The first integer after e is 3. That means from 3 to infinity. It's still fine. And I can even change this one. If we're not really looking at the few first finite numbers, that's not a problem. Everything after 3 works. Okay? That means this was just the proof of decreasing. We did satisfy all of the conditions. This alternating series is convergent. Convergent by AST. Okay, that means this is the way to use it and to state that the alternating series is convergent. But remember, we can't conclude divergence by AST. Okay, what we also have in this section, let's see this. We do have something like alternating series estimation theorem. That means, as I said, we can definitely conclude that the alternating series is convergent when we satisfied all of these 3 conditions, hypotheses. We can't really evaluate the sum, but what we can do, we can try to estimate. I mean, we can't really compute exactly, but we can try to estimate the sum of the convergent alternating series. I mean, let's see what we will do. I can show you a few things. Oh, okay. Yes, we can see this. That's what we have. The partial sums, of course, are S sub n, S sub 1, S sub 2, and so on. Of any convergent series can be used as an approximation of the total sum. Okay. However, we always have a little bit of error, and we have to know how good is this approximation, which we will try to estimate the accuracy of this approximation. That means what we will try to do. We will try to approximate the total, the finite sum, as a partial sum. That means let's look at this, my weird lines. I will try to explain this. Having alternating, but again, we're just talking about the convergent alternating series. Yeah? We have to have this part. Okay, that means the entire line, we can see this one, the long line, will represent the entire sum, S. Yeah? That's the sum, which of course I don't know. Oh, I wanted to write a little bit nicer S. Okay, that means this is the entire sum. We know that it's convergent because B sub n is positive, limit 0, and it's decreasing. That means that S exists. We don't know. But what I can do, I can definitely compute the partial sum. Like, let's say I will stop at B sub n. This is S sub n. Okay, that means I'm like, because I can always take like 10 terms, 50 terms, and I can add, subtract, and get the partial sum. And now what I'm trying to tell you, that the S, the long line, it's almost the same like S sub n. Yeah, you can see this, which you will probably tell me, oh, we do have this small difference. Yes, you can see that gap. And this is that gap, which means this difference is when I take the entire sum, which I don't have it, and subtract S sub n. Okay? That means this is my, and we will call like a remainder, or we will call a remainder, or we can say error. Okay, this is my error, because it is like error. Yeah, that's the error in this estimation, having the whole sum and the partial sum. Okay, and now we have to know how to approximate the size of this error, the size of this short line, okay? And now, if I will have the entire sum and I can compute the partial sum, like whatever partial sum I would like to take, I can just subtract s minus s sub n. But of course, that's not really the point, because I don't think we will have s. Because if I will have s, why I even have to like approximate something? That means without having an s, the entire sum, we still have to know how to approximate that, the size of this error, the accuracy of this approximation. Because if we can see if the s sub n is like really, really long, let's say here, I will have this only this small part as an error. Yeah, that means this error could be quite small. Okay? That means let's see how we can approximate that number, because that's actually the estimation theorem. Let's see what we will have. That means this, I can maybe write, this error was the entire sum minus the partial sum, okay? And the entire sum, of course, is my infinite series. Oh, actually, I did put s here. That means I will try to like play with these numbers. That means s means the entire sum, s sub n means just the partial sum, which means I will end up with b sub 1, b sub 2, b sub 3, b sub n. Okay, let me actually put the s, and this is s sub n. That we can see, because they are almost the same, right? Just the end of this expression is different, but the entire sum is b sub 1 minus b sub 2 plus b sub 3 minus b sub 4, and so on. And we can see we actually have, because we're going to the infinity. The partial sum, we will just end at b sub n. And you can probably notice I can cancel out some of the terms. B sub 1 will be positive, negative, and then opposite, negative, positive, and so on. That means I will cancel almost everything, but up to that. But I will end up with the next term, because the entire sum still includes b sub n plus 1, b sub n plus 2, and so on, right? Okay, but we can see this is interesting. That error, that remainder, that short line, it's equal to the next missing term. I mean the term that I'm not counting, because I'm only taking up to b sub n. And I can even say it will be even smaller than that term, because you see I'm actually subtracting the next term, because it's smaller and smaller, and we know we're subtracting. That means let's look at this. I can say that my error in this estimation, the difference between the entire sum and the partial sum, it's less or maybe equal, if these numbers are so tiny, to the next term that we didn't really use it. Okay? That we can see the size of the error is smaller than b sub n plus 1. Yeah? That means this is the absolute value of the first like neglected term, the term that we didn't use, because we will always use the term up to b sub n. Like let's say b sub 10, b sub 100. Okay? That's what, like, let's say if I will say that the sum, the entire sum, it's almost the same like s sub 10, like just taking a 10 terms. Then somebody asked me, what is actually the difference? Yeah? What will be the difference using just the 10 terms in the approximation of the entire sum? We can say the difference will be smaller than the next term, b sub 11. Okay? Because we can see always that, because we didn't use the next b sub 11. Okay? As we can see, and b sub 11 is relatively easy to find, because it's just b sub 1, b sub 2, b sub 3. We can compute b sub 11, no problem. That's we can see without having the entire sum, we kind of know what is the size of this error. Yeah, it's quite nice, powerful theorem also. Okay, let's see. This is also beautiful proof. Yes, okay, this is the alternating series estimation theorem. Okay? We have to have, again, alternating series. Of course, the sum satisfies all of the conditions. We remember positive, 0, and decreasing. Then means that it's convergent. Okay? And then if it's convergent, the S exists. Then the estimation in the error, in the approximation, looks like that. S minus the partial sum, it's always less than B sub n plus 1 if we're using S sub n. And we can see always one number more. Okay. And let's see how we can solve problems. This is like a little bit of proof I type for you. You can pause the video and check, but I think the other slide was quite clear. And I did copy this because, and we can maybe looking at this diagram, we can also prove, like let's say I will approximate that the entire sum, it's almost the same like S sub 5. But we can see this is S sub 5. That means this is the difference. Okay, that will be that error. Yeah, because we can see I'm supposed to be here and I'm here. Okay? Of course, but what I know, that the size, let's see, the size of this difference, the sum minus S sub 5, it's always less or equal to B sub 6, right? And let's check, B sub 6, this is the pink line. That's the B sub 6. And can you see my line, the bottom one, which represents the difference? This line represents the difference, of course, absolute value. We can see this line is definitely smaller than the B sub 6, the first term that we omit. We didn't use it. Yeah, that means this definitely works. If we will put 4 and 5, 3 and 4, it will also work. Okay. Enough of proofs. Let's actually look at your exam type, quiz type, assignment type question. What minimum number of terms of the series -1 to the n over 10 to the n times n factorial do we need to add in order to find the sum with the error less than 0.000005? Okay. Yeah, we probably think it's crazy, but let's see. Oh, okay, that's me what I have. I did type a little bit. That error, yes, this is this error. Okay, we know the theorem. Yes, my error, my approximation must be less than, and I can actually write point. Okay, I did type a little bit, 0.0. Actually, that number, because I don't think we like 0.0005. It's actually 5. Let's change for fraction, because this is fraction and I have to deal with this. 1, 2, 3, 4, 5, 6 zeros, which is 1,000,000, right? I can definitely simplify because I can divide 5 by 5 and 10 by 5, which means I will have 1 over 200,000. Okay, that means this is the same number, but I think we will like better a fraction. Okay, that's what I'm looking for. I have to find minimum number of terms, which means n minimum is important. Right? Like S sub n, I have to find n. We're looking for n. Okay? That, of course, we will satisfy the desired error, but I know based on my theorem that this error could be approximating by the b sub n plus 1 term. That means what I have to do, my job is to find the term b sub n plus 1 to be less than 1 over 200,000. And now, looking at the main formula, I hope we can see that b sub n is everything except that. Yes, we remember for the testing, or if it's convergent, that means it's simply 1 over 10 to the power of n factorial. And we don't have to really prove it. It's that b sub n is 0. I mean, limit is 0 at infinity. B sub n is decreasing, and b sub n is positive. That means it's definitely convergent. The alternating series is convergent, then the sum exists. Okay, that's why I'm not even saying that thing. It's definitely that. Okay, that's what we will do. I will take this b sub n and I will step by step substitute instead of n1 and check the value, instead of n2 and check the value. And what I'm looking for the number less than this, and then I will make some conclusion. Let's see, I think I type this. B sub 1 will be just 10 to the power of 1 and n factorial. 1 factorial, which is 1 over 10. This is definitely much bigger, okay? Because if the denominator is smaller, the whole fraction is bigger. Okay, this doesn't work. B sub 2 is 200. I hope we agree with this because it's 10 to the power of 2 and 2 factorial. 2 factorial is 2 and 2 times 100, 200. Okay, again, not a helpful number, because I'm looking for the term, that's what I'm testing. Okay, I want everyone to follow this. Okay, b sub 3. B sub 3 will be 1,000 times 3 factorial. 3 factorial is 6, 6 and 3 zeros. Okay, 6,000. Again, 6,000, it's not, I mean, in the denominator, it's still not giving me the smaller fraction. And what about b sub 4? Oh, interesting, b sub 4. 10 to the power of 4, of course, will be 1 and 4 zeros, and 4 factorial is 24. 24 and 4 zeros. Great. Now I can say that this term is definitely smaller because denominator is greater. Okay. Okay, that means b sub 4, now we have to be really careful to make the conclusion. B sub 4 is the term that is less, yeah, like we can see, less than my desired error, which means this quantity is 4. That means, can you tell me what is the answer? What is the minimum number of terms that we can add together and say the difference between the whole sum and the partial sum will be less than this? That means if n plus 1 is 4, what is n value equal to? Of course, it's always 1 less. Yes, that means this will be 3. That we can say is just enough to add 3 terms, and the difference between the entire sum and the partial sum will be less than this. Quite good approximation, and just not many terms. And I type this for you. Since the 4th term is less than the desired error, we need to add 3 terms. You remember, we always adding 1 less, because the b sub 4 is the term that we didn't use in our partial sum. That means theoretically, any number greater than 3, it's okay. Because if we will think like common sense, logically, if I will keep adding the terms, I'm making the error even smaller. Let's say I will add 100 terms. Of course, the error will be teeny tiny, will be less than this one. Because what's happened, I didn't compute, but b sub 5 will be also less. B sub, oh, I don't want to mess up. B sub 6, all of the other terms will be less, much less than the desired error. But the first one that we have to stop and make the conclusion is this one. So this is the answer. And you will probably see in your question, we always have to ask, we always have to include the minimum number of n. because 4, 5, 6 is also correct, but the lowest number is 3 because based on my theorem. Okay, let's solve one more and we will be done for today. Oh, almost the same question, you see? Just different formula. What minimum number of terms of the alternating series -1 to the n over n times 5 to the n do we need to add in order to find the sum with the error less than 0.0001? Okay, so I will do right away. Did I type? I typed something. Okay. I will write this number 1, 2, 3, 4 zeros. Okay, 10,000. That's mean again. This is the error, which means it's the difference between the actual sum and the partial sum, and we know that is less than the next term, b sub n plus 1. This is 10,000. Okay, who can tell me what's the formula for b sub n? B sub n. Can you tell me the formula? What formula I will be testing? I know I didn't ask many questions today, but at least we remember b sub n, it's everything except the -1 to the n. It's yes, thank you. Thank you, Roger. It's n 5 to the n. Okay, that's me. Let's start working. B sub 1, I will substitute 1. 1 times 5, 1 over 5. Way too big. Okay. B sub 2 will be 2 and 5 to the power of 2, which is 50. 1 over 50. Way too big. Okay. B sub 3 will be 3 and 5 to the power of 3. 5 times 5 times 5. I don't think this is 10,000. Or even more, because as soon as the denominator is greater, the whole fraction is smaller. Okay. B sub 4, it's 4 times 625. Is this 10,000? I don't think. This will be still smaller. If the denominator is smaller, the whole fraction is bigger. And what about b sub 5? It's 5 and then 625 times another 5. That means now we have kind of 5 times 3,000. Do you think 5 times 3,000, it will be greater than 10,000? This will be, yes, that means if the denominator is greater, the whole fraction is smaller. Okay, that means I got this. We catch the number. That means who can tell me what is the answer? What is the minimum number of terms? If this will be multiple choice, thank you. That means please remember, do not answer, we can see, do not answer 5. Okay, always one number less, because 5 means n plus 1. N must be. That means remember, this will be the option on the test. Okay.